We learned yesterday about a discovery that was made about 200 years ago by Hans Christian Ørsted. Pretty simple discovery, but a pretty important discovery. That discovery simply says that electricity generates magnetism. If you have an electric current, which is really just moving charges, if you have an electric current, it will generate a magnetic field. Now, we know what the magnetic field, we've known what the magnetic field looks like surrounding a bar magnet. Kind of looks like those butterfly wings almost surrounding a bar magnet. The magnetic field that surrounds this moving charge or this wire that carries an electric current would be circular. Now, when we say that, we don't mean like one circle. We mean a three-dimensional series of concentric circles. If we have a charged particle, a negatively charged particle that's moving into the page, it's represented by the X, then there's a magnetic field line that looks like this. And then there's another one that looks like this. And then there's another one that looks like this. And so on and so on and so on. What do you notice about the spacing of these field lines? Christian, what do you notice about the spacing of those? Yeah, they gradually get bigger, further and further apart from one another. What does that tell us about the strength of the magnetic field? As you get further away from the current that causes the field, it decreases, it gets weaker. I mean, that makes sense, right? As you get further away from whatever's causing it, the weaker that field is going to be. Now, we also have to be familiar with how to find the direction of this magnetic field. And that's what we use this wire grasp rule for. The first of three hand rules that we're going to learn, the wire grasp rule, says you got two variables. You got a thumb and you got fingers. You're going to bend your fingers. Make sure you keep your thumb and your fingers 90 degrees to each other like this, and then bend your fingers. How much do you bend your fingers? It doesn't matter. A little bit, a lot, it doesn't matter. It doesn't make any difference. You're still going to get the same answer. We're going to stick our thumb in the direction of the electric current. Or if it happens to be just a charged particle moving through the air, you're going to stick your thumb in the direction of the moving charge. Whatever, charge, current, whatever. Okay, same thing. Our bent fingers are going to point automatically, and I say fingers, I mean the fingertips, right? Your bent fingertips are going to point in the direction of the magnetic field that is caused by the moving charge or caused by the current. So let's look at the example that we just did above here. We're going to say this is a negatively charged particle, which means we use which hand, left or right? Left hand. If it was a positively charged particle, we'd do the same thing, but we'd use our right hand. That's all. It's the only difference. This is negative. We're going to use our left hand. We're going to stick our thumb 90 degrees to our fingers. We're going to stick our thumb into the page. Okay, that's for me, that's this way toward the front of the room. For you guys, it would be down toward the floor, according to your page, right? Doesn't make any difference. The answer's still going to be the same. Thumb into the page. Bend your fingers. I'll bend them a little bit. Which way do my fingers point? Well, they're pointing left right now, but that ends up meaning counterclockwise, yeah. Ends up being counterclockwise like this. You bend them more, you're going to find that they point down. Okay, you bend them a lot more, you're going to find that they point to the left or to the right. Doesn't really matter where your fingers are, as long as they're bent. They're going to be pointing counterclockwise any way you look at it. Now, I don't care whether you label it like this or you write it in words like this, counterclockwise, whatever. Make sense? Do a couple more examples that we did yesterday here. Let's say this was a positive particle right here. Positive particle, in this case, going which way? This dot means it's going towards us, right? It's coming out of the page or towards us. We've got magnetic field lines that look like this. They keep getting further and further apart. I'm going to draw just one, just so it doesn't clutter up my page here. In the end, all the magnetic field lines are pointing in the same direction, right? You don't have to do it for all of them, just do it for one. You have the answer for all of them. This is a positive particle, so we're going to use which hand, left or right hand? Right hand. Stick our right thumb 90 degrees to our fingers. Bend your fingers a little bit. Stick your right thumb out of the page. Bend your fingers, and my magnetic field is going to point counterclockwise again, right? Doesn't matter how much we bend them, it's going to point counterclockwise. Now, we reversed the direction of the particle. In the last question, it was going into the page. This one's coming out of the page. Yet we get the same magnetic field. Happens because not only did we reverse the direction of the particle, we also reversed the charge of the particle. And when we reverse two things, then it ends up kind of canceling out and giving us the original field. Let's look at this one. Let's make this a negative particle right here, moving to the left. Maybe it's a negative particle. Maybe it's electrons moving through a wire. in an electric current. Doesn't matter. Sometimes it's useful to come up with a little manipulative for this. Maybe your pen. Pen works well because it's got the little point on the end of it, and you can aim that in the direction of the current here. I'm going to point my pen to the left here, and I'm going to stick my thumb to the left, my left thumb because it's a negative particle, and I'm going to stick my fingers wherever. Where are they right now? Connor, where are my fingers right now? Above. And which way are they pointing? Yes, towards us, out of the page. So we're going to make that a dot above. Now, where are my fingertips right now? Where are my fingertips right now? Below. Which way are they pointing? Into the page. Good. Ariel, where are my fingertips right now? Behind it. Which way are they pointing? Up. So I'm going to draw a little arrow like this, a broken arrow up. Okay, Grace, where are my fingertips right now? In front. And which way are they pointing? Down. Stands to reason, right? If you figure out even just one of these, you can kind of trace it around and figure out the rest of them. I like to do the hand rule, the wire grasp rule, that is, for all four of these positions, though, because I figure if I do it once in one place and then just kind of trace it around, what if I made a mistake the first time? Well, then I'm going to get all four of these wrong, right? Okay, if I make a mistake the first time and then use the wire grasp rule to figure out the second, the third, and the fourth, I'm probably going to catch my mistake, unless I make a mistake all four times. All right? Well, that's the first hand rule of three that you're going to learn. Now we're going to learn the second one. The second one we call the coil rule, or the coil rule for solenoids. A solenoid is a coil of wire. It looks something like this. Wire wrapped around in kind of a bunch of loops like this. When I draw pictures to use this coil rule for solenoids to determine the polarity of this, and that's what this becomes, right? It becomes an electromagnet with a polarity that is north and south. When I draw this, I will typically draw it so that there is a steel or iron or some kind of ferromagnetic core inside. The reason I'm going to do that is because, two reasons actually. One, because it actually strengthens the effect. If you have a ferromagnetic material inside this solenoid or inside this coil of wire, it actually makes the effect stronger because it stores it for a little while. If you have just a coil of wire, it generates a magnetic field, and it does generate a distinct north and south polarity, but as soon as you flip it off, it's gone. If you have a coil wrapped around a piece of steel, then as a new magnetic field is being generated by more electric current, you still have some remnant of the old magnetic field that's stored in this iron core, this steel core. So it magnifies the effect. That's one reason that I'll draw this ferromagnetic material inside this coil. The other reason is I think it's easier to see what this coil is supposed to represent. Right? If I draw this inside, you can see where the wire is, what's in the front, what's in the back, a little bit easier than if we don't have it inside. Just understand that as we do the analysis here today, there doesn't have to be a ferromagnetic material inside like this. I just draw it like that for a couple of reasons. We're going to use this coil rule for solenoids to determine the polarity or the direction of the magnetic field that's generated by this solenoid or by this coil of wire, whatever you want to call it. We could use the wire grasp rule, and usually I'm all about using one thing to answer as many different questions as we can. This is the exception. Okay, I'm going to use a specialized rule here for this one specific case of a solenoid because I think it makes it quite a bit easier. Now, there's a lot of similarities between the coil rule for solenoids and the wire grasp rule. One similarity, well, we use our thumb and our bent fingers, just the same as we did for the wire grasp rule. Another one, well, if we have electron current, we use our left hand. If we have conventional current, we use our right hand. But what's the difference? You got to be careful that you remember this. With the wire grasp rule, thumb pointed in the direction of the current, fingers pointed in the direction of the magnetic field. With this coil rule, it's the opposite. Instead of thumb pointing in the direction of the current, my bent fingers will point in the direction of the current. And instead of my bent fingers pointing in the direction of the magnetic field generated by the wire, my thumb is going to point in the direction of the magnetic field that's generated by this coil or this solenoid. Now, There is a magnetic field inside the solenoid. There's also a magnetic field outside the solenoid. When I use my thumb to find the direction of the magnetic field, it's the direction of the magnetic field inside the solenoid, which goes from not north to south, because that would be outside. It goes from south to north. Be careful with that, right? In just about everything we do, our magnetic field goes from north to south. Here it's from south to north, because my thumb's going to point in the direction of the field inside the solenoid, not outside. You don't need to copy down this picture, but I just want to represent what it looks like here. You can see that the current is, this loop here, it's kind of going up in the front, and then it's going to loop around down in the back, up in the front, down in the back. You can see this person's fingers here. It's showing, the fingers are pointing kind of down in the back, right? Well, they could point up in the front. It doesn't really matter. The fingers are pointing in the direction that that green electric current is going, right? And that person's thumb is automatically going to point to the right, which means the magnetic field line, as it's drawn right here, points to the right, inside the coil, which means this would be the south end of this coil, and this would be the north end of this coil. Again, because the magnetic field inside goes from south to north. Now, if you were to extend this magnetic field around it would look like this, from north to south, outside. But we're directly trying to find the magnetic field inside. The direction of the thumb is from south to north. We'll do some examples here, so don't panic about copying down this diagram that's on the board here right now. Let me draw a core. Although, again, we don't have to have that. It just makes it a little bit easier to visualize it. And let me draw a wire that goes around like this. This is a battery down here. This battery has a positive terminal and a negative terminal. The long end always represents positive, and the short end always represents negative. Now, if we want to analyze this using electron current, which I suggest that you do, then the electrons would flow counterclockwise, away from the negative end like this, up in the back, down in the front, up in the back, down in the front, and then around counterclockwise. If you were, for whatever reason, wanting to analyze this using conventional current, and remember, it's not actually positives that flow through this. It's really negatives that flow through this, and that's why I suggest that you use electron current. Then you would just have it the other way around. Your conventional current would go clockwise. Does that make sense? Now, how do you get the right answer using either way? Well, if you use your left hand, so if you use electron current, use your left hand, conventional current, use your right hand, your thumb's going to point in the same direction either way you look at it, as long as you're consistent. I'm going to use the flow of the electrons because that's the way it really goes. And we're going to see which way the magnetic field points using the left hand. Now that we see the problem, now that we've got our little manipulative of the coil that we just made with a piece of paper, I want you to look at the word front. You're always looking at the word front on this little manipulative, okay? Always. Okay, even if you're trying to show me something, okay, trying to show me something that you do with your hand, don't change the orientation of this. You're always looking at the word front. Let me figure out the way it's supposed to look. You keep looking at the word front. Now, what I want to do with my left hand, because I'm going to use electron current here, is I want to stick my left fingers, remember, fingers go in the direction of the current this time, not thumb. Fingers go current. I want to stick my left fingers either down in the front, or if it's hard to twist your body that way, you can stick your fingers up in the back, because it's the same thing, right? The current's going down in the front, as you can see on the board there, and it's going up in the back. So whatever works for you, make sure it's one or the other, though. Now, everybody's got their fingers either pointing down in the front or up in the back. That's great. Which way is your thumb pointing? It's pointing to the left, right? That means the magnetic field inside this coil is going to be pointing to the left. That means the polarity of this coil becomes what? This is what? North or south? North, and this is south. So we've got an electromagnet now with a distinct north pole and a south pole. North on the left, south on the right. We could use the wire graspel to do this. I'm just suggesting that you don't, because this coil rule ends up being a lot easier to determine the polarity. Let's draw another one here now. Let's draw this one such that we have let's see, the wire going like this. Battery like this, positive terminal, negative terminal. Isn't that the same thing? Electrons going counterclockwise like this. Doesn't this end up being the same? What's different about this from the second one than the first one? The wire's kind of reversed there, right? We have the current going up in the front, down in the back, up in the front, up in the front, down in the back, and so on, right? So it's backwards here. We want to do this one. We want to, again, look at our coils that we just made a few minutes ago. Look at the word front. Everybody look at the word front. Put your fingers either up in the front or down in the back. It doesn't really matter. Whatever's easier for you to twist your arms and wrists to do. Which way does my thumb automatically point when I go up in the front or down in the back? Thumb points to the, Christian? To the right. So that means the magnetic field is going to point to the right here. Even though the current is going the same way, counterclockwise, the magnetic field is reversed with a north pole and a south pole right there. Let's try another one. Here's my core again, which we don't really need, but we draw it in there just to make it a little bit easier. Which end is the positive end? Which end is the negative end? Bottom side is positive, top side is negative. If I'm talking about the electron current, that's the way that I want to do it, then the current is going to go which way? Clockwise or counterclockwise? It's going to be counterclockwise. It leaves the negative, comes around here. Goes to the left in the back, to the right in the front, like this. All right, this time I want you to turn your coil that you made with a piece of paper a little while ago. Still look at the word front, but turn your coil so that it's oriented vertically. Then I want you to stick your fingers, your left fingers, to the right. In the front, that is. Or if it's easier for you to do it in the back, make sure they point to the left. Which way does my thumb automatically point? Thumb automatically points down, which means the magnetic field inside the coil goes down, means this is the north or south. North, and this is the south. Is that good? Okay, I'm going to have you do one yourself now, without my help. We'll check it over as a group in a couple minutes, but for now, you're going to work on it yourself. So we got a battery set up like this, above the coil this time. This is a positive end, this is a negative end. If I'm dealing with the electron current, which way is it going to go? This way or this way or the other way? First way or second way? It's going to go the first way, right? So that means it's going to go down in the back, up in the front, down in the back, up in the front. All right, see what you can do. All right, let's have a look. Once again with your manipulatives, which, by the way, you're welcome to use on a test, including a diploma exam. The only thing would be on a diploma exam, you can't bring this in with you. You have to make your own when you're in the middle of your diploma exam. There's nothing wrong with that, though, right? Take a piece of scrap paper, roll it up, write the word front on it. As long as you do it in the exam room, you're fine with that. For your test, as far as your test goes, I couldn't care less if you bring this in with you, as long as it doesn't have other writing on it besides the word front. All right, so I'm looking at the word front. I know that my current goes up in the front, so my fingers are going to go up in the front, or if it's easier, make your fingers go down in the back, either way. Up in the front and or down in the back. My thumb's going to automatically point to the plexus, to the right, which means the magnetic field points to the right, which means this end is north or south. This is south, and this is north. The magnetic field goes from south to north inside. If I was to continue it around, then we would get it from going from north to south, right? Because then it would look like a bar magnet. Is that good? You will, I promise you this, on your unit test, which is coming up the last week before Easter break, not this week, not next week, but early the following week, you will, I promise you, get at least one question, probably more than that, but at least one question where you have to do the wire grasp rule, and you'll get at least one question, probably more than that, where you have to do the coil rule. You will see both of these rules so far. If you take a look at page 4 in your example question book, you see two pictures. One, you see up on the board right now. What is this? It's a speaker. Yeah, it's a speaker that you would see in a ceiling if you were to take that apart where the announcements are made. It's a speaker that you would see in the stereo in your car. It's a speaker that you would see on a much, much smaller scale in your earbud that you listen to your iPhone music with. In the end, they're all pretty much the same. The way that a speaker works, especially now that everything's digital, music is all stored digitally, we speak into a microphone, or you sing into a microphone, or you play music into a microphone, it gets converted to an electrical signal. And then in some kind of electronic device, some sort of computer, it gets converted into a series of ones and zeros, a digital signal. Like every single bit of music, literally, every bit of music is stored as ones and zeros, which are called bits, by the way, for those of you who didn't get that. And then when you go to play it, that digital signal, those ones and zeros, are converted back to an electric current. That electric current changes a lot. It might change in direction, depending upon the ones and the zeros. It might change in strength, depending upon the ones and zeros. But you've got an electrical current. So the electrical current that's been generated by your iPhone is proportional to the music or the sound that was originally recorded wherever it was recorded in whatever studio. That electrical signal goes through the wire to your earbuds, if you have wired earbuds, and then it goes through this coil of wire that you see right here. That generates a magnetic field and produces an electromagnet. Now that electromagnet changes a lot. Sometimes it changes in the polarity. If the current reverses, the north and south polarity reverses. If the strength of the current changes, depending upon the music, then the strength of the magnetic field changes. But you've got, nonetheless, at every instant in time, a magnetic field produced by this coil. That magnetic field causes the permanent magnet that surrounds it to move, either left or right. A little bit to the left, a little bit to the right. A lot to the left, a lot to the right. It depends upon the strength and the direction of the electric current that's going through this. Now that permanent magnet is attached to a cone which is often made like of a paper or a cardboardy material, kind of a felt material. And as that magnet goes back and forth because of the electric current that's changing in magnitude and direction, the cone goes back and forth. And as that happens, it creates, if the cone is going towards you, it creates a high pressure zone in the air. If the cone is going away from you, it pulls back on the air and creates a low pressure zone. What is sound? What is sound but varying pressures in air? That's all it is, right? So as you push this cone back and forth real quickly, depending upon the electrical signal that depended upon the bits that came from your iPhone, that depended upon the original music that was produced, as this goes back and forth because of all that, then it regenerates the original sound that was produced via high pressure areas and low pressure areas in the air, and then ultimately high pressure areas and low pressure areas in your eardrum, causing your eardrum to go back and forth. That's why you hear the sound. That's why the speaker generates this sound. Does that make sense? Yep. I'm sorry? Just zeros and ones. Just zeros and ones. It's called binary, and everything's stored in zeros and ones. It's a language, essentially. We have a 26-letter alphabet to describe everything, right? In English, right? In binary, you have a 2-number alphabet, essentially, that stores everything. And how that, yeah. So how exactly, yeah. Instead of having 10, well, even better, right? Like Ariel says, we have 10 numbers, 10 digits that represent every single number. Binary has 2. When we have 26 letters that represent every single word, they have 2 numbers that can represent every single word as well. The ones and the zeros, like, it's not like, if you were to look at the way it's digitally stored, you're not literally going to see a 1 and a 0. It's kind of like the domain. We represent it by an arrow, but you're not literally going to see an arrow in this ferromagnetic material, right? Nor are you going to literally see a 1 in this, right? We represent it by a 1, and we represent it by a 0. A 1 generally represents an electrical signal of usually 5 volts. and a 0 represents an electrical signal of 0 volts. So that's how we represent basically on and off. Okay, a code. It's a code of on and off, and then that signal is produced by the music in this case, and then produces in turn more music. Right? It's a code, just like we have. You look in the newspaper, you see the crypto quote. You guys know what I'm talking about? Where one letter represents another, and you got to figure out what the word is. It's almost the same thing, right? It's just a code that can be used to store multitudes of information, right? Question? Well, yeah, that's all the speaker is. But understand, when we're talking about this digital thing, that's not the speaker, right? The speaker is analog, but it's the digital signal that gets converted to the current, which powers this speaker. But yes, that's all the speaker is. Now, in terms of making a good speaker versus a poor quality speaker, probably depends upon the strength of the magnetic field. I would imagine the stronger, probably the more effective it's going to be, because the more sensitive it's going to be to variations in current and the material of the cone and the size of the cone, and probably all kinds of things that are going to make it better or worse, but that's the essence of any speaker. Now let's take a look at another one here. What do you think this is? Looks kind of like a fire alarm, right? Could be a doorbell. Okay, it's kind of an odd doorbell because it'd be one that you'd have to push the button and hold it to get a ding, 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 as opposed to a ding dong. But in the end, it could work. It's more of a fire alarm. When the switch gets closed, and the switch doesn't get closed because you're physically holding it, the switch gets closed because you open it and it automatically, you close it, and it automatically stays closed. Right? The switch is closed, electric current starts flowing through this circuit. Leaves the negative end of the power supply, comes back to the positive end of the power supply. So you see the current goes around like this, goes through this metal material right there, goes into this make or break spring right here, this make or break contact, I should say, right here. Now this make or break contact is touching, the contact is made with this wire that comes around here and then goes through these coils. What happens when the electrons go through this make or break contact, through this wire, and then goes around those coils? What happens to these two coils? It creates a magnetic field, right? It creates a magnetic field. Now the current keeps going through here, through the coil switch, and then back, and keeps going, right? Now, as these two coils become electromagnets, they can become magnetized as a result of electric current, they're going to attract this piece of steel right here, this thing that made contact with the make-break contact. So this thing is now going to be pulled over here. Contact is now broken. But along with it, it pulled this piece of steel. It's not pulling this directly. It's pulling this piece of steel right here, which pulls with it this wire right here that was touching the make or break contact. Does that make sense? Now, attached to this piece of steel right here is this hammer. As it pulls this piece of steel with it, it also pulls the hammer with it. What happens? The hammer gets pulled to the right, and we hear we hear kind of a bell. What exactly do we hear? Ding. It's not a very good fire alarm if all you hear is one ding. You miss it, and you're talking, and all of a sudden, house burns down or your school burns down, and you didn't even know the fire alarm went off. We need it to go ding, 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 ding. So what do you got to do? Somebody sees a fire, you stand over there by the switch and do this, back and forth, so that it goes ding, 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 ding. No, when you open the switch, it keeps going, right? Why? Well, because now when this hammer and this purple piece of steel and this blue wire right here that was in contact with the make or break contact, as it gets pulled over to the electromagnet, contact is now broken. The current turns off. As the current turns off, what happens to the electromagnet? Turns off. This spring right here pulls it all back to the make or break contact. Makes contact again. Current starts flowing again. Remagnetizes the coils. Pulls everything over again. Ding. Turns everything off. spring pulls it back. Current starts flowing. Remagnetizes the coils of wire, pulls it all back over, ding, breaks the circuit, spring pulls it back, and so on and so on and so on. I mean, that happens pretty quickly, several times per second, right? So that you hear ding, 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 as opposed to one ding. Okay? But that's the basic principle of what's happening.